Hello everybody, my name is Wei Xing. Welcome to my virtual booth. In this video, I'll be talking about my research, which is on subtype-specific prediction of treatment outcome in pediatric acute lymphoblastic leukemia. So what is acute lymphoblastic leukemia or ALL? ALL is a cancer that affects lymphoid lineage blood cells, which are descendants from the common lymphoid progenitor cell. The aim of our research is to improve treatment outcome prediction in pediatric ALL through the use of time series gene expression data. We hope to achieve two main objectives. The first is to reduce the number of deaths due to relapse, and the second is to reduce the cytotoxic side effects that are frequently associated with overtreatment in chemotherapy. Our biological hypothesis is that the gene expression profile is a measure of the average gene expression of all leukemic and normal cells in the sample. A patient that has a greater treatment response would experience a larger decrease in proportion of leukemic cells over time. This is reflected by a greater shift in his gene expression profiles in response to treatment. In addition, we also hypothesize that different ALL subtypes have different basal rates of decrease in the proportion of leukemic cells. Hence, we propose that ALL subtypes should not be modeled together as a whole. We propose using a subtype-specific model where individual prediction models are created for each subtype. However, separating patients by their subtypes results in a few subtypes with small sample sizes. This prevents the use of machine learning algorithms, which are prone to overfitting on small training datasets. To overcome this issue, our model adopts a simple mathematical approach. In each individual subtype-specific model, we follow the same three-step framework. We first select for probe sets that show a large response to treatment. Second, we compute transcriptomic features from a patient's day 0 and day 8 gene expression profiles. Thirdly, we estimate a patient's probability of achieving continuous complete remission given his or her feature values. We explain more on the transcriptomic features. In this figure, the red arrow represents a patient's treatment response. The arrow from the leukemia centroid to the normal centroid represents the general treatment direction. The ERM ratio is the length of the green arrow divided by the length of the purple arrow. The ARM ratio is simply the length of the red arrow divided by the length of the yellow arrow. And phi is the angle θ1 divided by the angle θ2. All these three transcriptomic features are measures of a patient's treatment response. We estimate a patient's probability of remission given his feature vector X and subtype S by first computing conditional probabilities of remission given each feature J. We illustrate how to compute a conditional probability of a feature value by using this example here. So we consider a patient with an ERM ratio of Xj, which is represented by this blue dot. We compute the probability of remission given Xj by considering first how many remission patients a patient is better than. In this case, this is 4. We then take this number and divide it by the total number of remission patients in our training dataset. In this case, this is 5. Hence, we obtain a probability of 0.8. We established the following results in our research. First, we showed that transcriptomic features are predictive of treatment outcome in homogeneous subtypes. Second, we showed that our subtype-specific model outperforms existing methods in treatment outcome prediction. Third, we show that our subtype-specific model identifies low-risk patients with high precision. These patients are prime candidates for de-intensification of chemotherapy. Thank you for your attention. Please feel free to contact me at my email for any further discussions.